Welcome back. In the last session, we have seen how to reshape a torch tensor. We saw that we are calling view method, and this method would reshape our torch tensor. Today we are going to discuss a very important topic. This is the topic of computational graphs in PyTorch. As we know, in other deep learning frameworks, we also deal with computational graphs, like in Keras or in TensorFlow. But in these frameworks, the computational graphs are fixed. So you create a model, and as in Keras, for example, you define, for example, if it is a neuronal network, you define different layers, optimizer, you define loss function, number of epochs, the batch size, and then you call compile. If you call compile, the runtime will create a computational graph of this model. And this computational graph is fixed, so you cannot change. If you call model.fit, it will execute the computational graph, and during runtime you cannot change it anymore. It's fixed. And PyTorch has created something completely different. The creators of PyTorch have decided that they need a flexibility to change the computational graph at a runtime. How did they accomplish this? They have created a component which is called autograd.Variable. This is the main building block of a computational graph in PyTorch. How it works? Let us see. Let us execute this next cell. So first of all, we are creating autograd.Variable. We are passing two parameters. One parameter is actually data of this autograd.Variable. This is a torch tensor of size 3. And then we can pass the second argument, which is requires underscore grad, which is the meaning requires gradient true or false. It means following. If we say if we say requires grad true, we are saying that this autograd.Variable should track how it was created. This is very important. So we can print out here the data which is inside of this autograd.Variable. This is simply the tensor of size 3, 1, 2, 3. Then we are creating the next autograd.Variable, which is y. Autograd.Variable y, the same. We are passing as argument data. This is the first parameter. Then we are passing the second parameter, requires gradient true or false. We are passing true. And then we are adding up x and y. And here we are printing the data in the component z, which is the sum of x and y. So this is the sum. So we just have summed up element-wise two vectors. But here, what is very interesting is here that we can also see how z was created. If we write z dot grad function, grad underscore fn, and print out this operation, we see that z was created by add operation. It's very interesting. Let us see next example. Here we are summing up the components of the z vector. So z vector we have created as a sum of x and y. This is 5, 7, 9. If we add up all those elements, we are getting 21. Nothing very interesting and special. But if we call in the next step, if we call s grad function, grad fn, we see that it was created as a sum. So the PyTorch knows exactly for every variable how it was created. Here we are with the next example, and here we have a function s. This function s is a sum of two variable vectors of size 3. So we are summing up this vectors element-wise. So we are summing the first element of vector x with the first element of vector y, the second element with the second, and third with the third. So now, if we create partial differentiation, so if we differentiate s with respect to x0, for example, due to the rules of partial differentiation, we would deal with other variables other than xy as with the constants. So the partial differentiation for s, for the function s, with respect to variable x0 is 1. Let us see how it works with PyTorch. So first of all, let us recap that s was the sum. This is actually the sum element-wise. And here we are calling backward. And backward means start back propagation from this point, backward. So it's starting back propagation. So we have the function s, which is the sum, and then we say backward, and here we can pass the argument retain graph true. I will not go into details, but it's optional actually. So here if we run this next cell, what we see here is following. So first of all, we are printing vector x, and we see here's nothing special with just printing out this vector. But now, if we print out the gradients, not the gradient function as in the previous time, but now we can print out the gradient. Meaning gradient is the value of if we create differentiation, if we differentiate the function at a special point, we are getting also the value of this partial differentiation. And here we differentiate this function with respect to variable x. X containing x is consisting of three variables: x0, x1, x3. So if we differentiate partially with respect to x0, we are getting 1, and then again with respect to x1 we are getting 1, and with respect to x2 we are getting 1. We saw that this is a very simple function. If we create partial differentiation, it would be 1 and all other variables would get zeros. Therefore we have here 1, 1, 1. The same thing if we create differentiation, partial differentiation with respect to y, because y is also as x, a simple plain variable here without any coefficients or exponentiations. It's just 1, 1, 1. But what will happen if we call again backward? And then we call again x grad and y grad. You see, it was updated. So now we have here 2, 2, 2, and for that was for x, and for y the same, 2, 2, 2. What has happened? Let us call again backward and again print out. Now it's again has again changed. It's 3. The reason is every time you call backward, the gradient property is accumulated. This is a technology of PyTorch, which is used for special there are some models where it's very convenient to use. In this introductory session we will not use it, but it's important to know that every time if you call backward, the gradient will be accumulated. Next important point is how to preserve the computational graph. As you already know, the autograd variables are consisting of 2 components. One is the data, another one is the grad.Fn, gradient function. So with the data, you can get out of the gradient of the autograd variable, you can get out the data, and with grad.Fn you can get out the function how this variable was created. Let us execute next cell. In this cell we are creating 2 tensors of size 2, and then we are summing up these tensors. It's very simple. So we are getting actually tensor of size 2 by 2, sorry. So now let us execute next cell. Here we are creating autograd variable x out of x and autograd variable y out of y, and we say in both times requires gradient true. So now we can sum up these variables, var x plus var y, and then we are printing out the gradient function, how it was created. Let us do this, and we see z was created with add operation, add backward. But now what we do is following: we are extracting the data out of this sum, just the data, and passing it to a new variable which is called var z data. And then we are creating actually new variable, new autograd variable, and passing this new data variable in it. And then we are printing out, and then we are trying to print out how it was created. So we are actually printing out new variable z dot gradient function. And then you see none. It's lost, because here if we are extracting the data, we have extracted only data but not the gradient function. And yes, then the computational graph at this point is already broken. So the grad.Fn was not passed, and we have retained only data but not the gradient function. And now if we try to call backward on this new autograd variable, new var z, which was created again with the data out of var z, we will get exception, because there's nothing there. Here we have runtime error, that the element of variable does not require grad and does not have a gradient function. This is the important point. Does not have a gradient function. Gradient function was lost. And last but not least, in this session, I would like to briefly mention the CUDA functionality of the Torch tensor. So, as you probably remember, the Keras and TensorFlow automatically detect whether you have GPU acceleration on your machine or not. And they will execute everything on GPU if GPU is available, or on CPU if GPU is not available. For PyTorch, you can very granularly decide what to execute on GPU and what to execute, which tensors you want to execute where, on GPU or on CPU. Here you have a check, and you can check torch.CUDA.is available. And this check you can run every time if you want to decide where to execute a tensor. If you want to execute a tensor on CUDA and CUDA is available, you just add CUDA function .CUDA, and then it will run this tensor on GPU. If you don't want to run a tensor on GPU, you don't add this CUDA function at the end, and it will run on CPU. This is very, very flexible. So in my opinion, the main advantage of PyTorch is its huge flexibility. Okay, I hope you enjoyed the session, and next time we are going to try something really practical. We are going to build up a linear model with PyTorch. See you then. Enjoy our sessions. Bye bye.